A warm welcome to everyone for a video presentation on the architecture of DBMS. This is belonging to the subject database management system. I welcome you all. I am Bharath M, of 4th semester Computer Science Engineering in Artificial Intelligence at Sri Venkateswara College of Engineering, Bangalore. The subject I'm going to speak about is database management system, and the topic is, as we saw, it's on the architecture of DBMS. First, let us have an introduction to DBMS. What is DBMS? A database management system, or DBMS, is a software that enables users to efficiently define, create, maintain and control access to databases. It serves as an intermediary between the end user and the database, ensuring that data is consistently organized and easily retrievable. DBMS are critical in various applications from business operations to scientific research, providing a systematic way to manage large amounts of data. Key benefits include data integrity, security, and concurrent access by multiple users, making DBMS a foundational technology in modern computing environments. What are the components of DBMS? DBMS is composed of several key components that work together to manage data efficiently. These include the database engine, which handles data storage, retrieval and update operations. The database schema, defining the structure and organization of the data. The query processor, interpreting and executing SQL queries. And the transaction management system, ensuring data integrity and consistency. Additionally, concurrency control mechanisms manage simultaneous data access, and database security features protect against unauthorized access. Together, these components enable reliable and efficient database management. This is about the components of DBMS. Next, let us look on the DBMS architecture overview. DBMS architecture refers to a structured framework that dictates how data is stored, managed and accessed. It typically comprises of three levels: the external level, representing user reviews and interactions; the conceptual level, describing the logical structure of the entire database; and the internal level, detailing the physical storage of data. This layered architecture ensures data abstraction and independence, allowing changes at one level without affecting others. Understanding these layers is crucial for efficient database design and management, ensuring a robust and scalable database system. Now, let us look at one-tier architecture. The one-tier architecture, also known as the single-tier architecture, is the simplest form of DBMS architecture, where the database and the application accessing the database reside on the same machine. In this setup, the user interacts directly with the database, making it ideal for local applications. However, it has limitations in terms of scalability and network access, and is less suitable for larger and more complex applications. This architecture is often used in standalone systems, small-scale applications, and during the development and testing phases of larger systems. This is about the one-tier architecture. Now let us continue going on after one tier to the two-tier architecture. Two-tier architecture, also known as the client-server architecture, separates the user interface and application logic from the database. The client layer contains the user interface and application logic, while the server layer manages the database. Clients send requests to the server, which processes the queries and returns the results. This architecture offers improved performance, security, and scalability compared to one tier. It is commonly used in applications where the database is accessed over a network, such as in departmental or small-scale enterprise applications. This is about the two-tier architecture. In the next, it is on three-tier architecture. Three-tier architecture, commonly used in large-scale applications, divides the system into three layers. that is presentation, application, and database. Here, the presentation layer is the user interface. The application layer contains the business logic and processing, and the database layer manages data storage and retrieval. This separation enhances scalability, maintainability, and flexibility. Changes in one layer do not affect the others, allowing for independent development and updates. This architecture is ideal for web applications and enterprise systems, supporting complex transactions and multiple user interactions efficiently. Fine. Now let us look on database schema. A database schema is a blueprint of how data is organized within a database. It defines the structure including tables, fields, relationships, views, indexes, and procedures. These There are three types of schemas. One is the physical schema, detailing the storage of data on disk. Logical schema, outlining the logical constraints and structure of the data, and view schema, which is representing the user interactions with the data. This schema ensures data consistency and integrity, enabling efficient data management and retrieval, and serving as a guide for database designers and developers. Here, it is on the data models in DBMS. Data models define how data is structured, stored, and accessed in a DBMS. Key data models include hierarchical model, which is organizes data in a tree-like structure with parent-child relationships. Network model, similar to the hierarchical model but allows many-to-many relationships, creating a graphic structure. Sorry, it's a graph structure. Relational model uses tables or relations to represent data and relationships, supporting SQL for querying. Object-oriented model integrates object-oriented programming principles, storing data as object with attributes and methods. Here, these models provide different ways to conceptualize and manage data, each sufficient for specific application needs and complexities. This is about the data models in DBMS. Now let us look at a relational model. The relational model organizes data into tables, that is relations, where each table consists of rows, which is tuples, and columns, which is attributes. Each table has a primary key that uniquely identifies each row and foreign keys to represent relationships between tables. This model supports SQL, which is structured query language for data manipulation and querying. The relational model's simplicity, flexibility, and use of table makes it widely used in various applications, ensuring data integrity and enabling complex queries and transactions. Its foundation on mathematical principles ensures consistent and reliable data management. In the next, we'll see on what is the data independence. Data independence in DBMS refers to the separation of data abstraction layers, allowing changes in one layer without affecting the others. There are two types of data independence. One is logical data independence and another is physical data independence. Logical data independence, this enables changes to the logical structure or schema without changing the application's view. It allows modifications to tables, views, or queries without affecting how data is accessed. Physical data independence allows changes to the physical storage structure without affecting the logical schema. It enables modifications to storage devices, indexing methods, or file organization without impacting the application. Data independence simplifies database management and enhances system flexibility and scalability. Next, it is on the DBMS languages. DBMS languages are used to interact with the database. The main language used is SQL, which is structured query language, which is divided into several sub-languages. First one is data definition language, DDL, used to define the database structure, including creating, altering, and dropping tables and indexes. Data manipulation language (DML) used to manipulate data within the database, including inserting, updating, deleting, and querying data. Data control language (DCL) is used to control access to data, including granting and revoking permissions. Transaction control language (TCL) used to manage transactions, including committing and rolling back changes. Understanding these languages is essential for effective database management and application development. Next, it's about the storage management. Storage management in DBMS involves how data is stored, organized, and retrieved on storage devices. It includes file organization, determining how data is stored in files such as sequential, indexed, or hashed. Indexing, that is creating and maintaining indexes to speed up data retrieval. Buffer management is managing buffers to reduce disk input-output and improve performance. Data dictionary management is storing metadata about the database, such as table and index definitions. File and record management, managing files and records including creation, deletion, and modification. Efficient storage management is crucial for optimal database performance and scalability. This is about storage management. Next, it's on query processing. Query processing in DBMS involves converting user queries into efficient execution plans that retrieve the requested data. It includes several steps. The first one is parsing, optimization, and execution. Efficient query processing is essential for ensuring fast response time and optimal resource utilization in database systems. Various techniques such as query optimization and indexing are used to enhance query performance. Next one is about transaction management. In DBMS, it ensures the ACID properties of transactions. Transactions are uh, units of work that must be executed automatically or atomically, ensuring data consistency. DBMS manages transactions through transaction states, including active, partially committed, committed, and aborted states. Concurrency control is managing simultaneous transactions to prevent data inconsistencies. Recovery management is ensuring transactions can be undone or redone in case of failure. Logging is recording transaction operations to facilitate recovery. Transaction management is critical for maintaining data integrity and reliability in database systems. This was about transaction management. Next, let us look at concurrency control. Concurrency control in DBMS manages simultaneous access to data by multiple transactions to ensure data consistency and isolation. It includes techniques such as locking and timestamping. This prevents issues like lost updates and inconsistent reads, ensuring that transactions are executed safely and efficiently in a multi-user environment. The next one is about recovery management. Um, Recovery management in DBMS ensures that the database can be restored to a consistent state after a failure. It includes logging, undo logging, redo logging, and recovery algorithms. Recovery management is crucial for maintaining data integrity and ensuring that the database remains reliable even in the event of failures. This is about recovery management. The next one is the security in DBMS. Security in DBMS involves protecting data from unauthorized access, modification, or destruction. This thing includes authentication, authorization, encryption, auditing, and access control. Security measures are crucial for protecting sensitive information and ensuring compliance with regulations. Its compliance with regulation. DBMS provides various security features to safeguard data integrity and confidentiality. This is about the security in DBMS. The next one is distributed DBMS. Distributed DBMS which is DDBMS, refers to a database system where the data is stored across multiple locations or nodes connected by a network. It offers several advantages including improved performance, which is data can be stored closer to users, reducing latency. Increased availability, data can be replicated across nodes, ensuring availability even when some of the nodes fail. Scalability is easily scales to accommodate growing data and user base. Fault tolerance, redundancy of data, and data distribution ensure fault tolerance. However, managing a DDBMS requires addressing challenges such as the data rust, deep, um, data consistency, concurrency control, and distributed transaction management. This was about the distributed DBMS. Next, let us look at the conclusion before we finish with the video. In conclusion, understanding the architecture of a database management system is crucial for designing and managing databases effectively. Key takeaways from this presentation include DBMS consists of various components that work together to manage data. Different architectures such as one-tier, two-tier, three-tier offer varying levels of complexity and scalability. The relational model is widely used due to its simplicity and flexibility. Data independence allows changes to be made to the database structure without affecting applications. Transaction management, concurrency control, and recovery management are essential for maintaining data integrity and consistency. Overall, a well-designed DBMS architecture ensures efficient data management and retrieval, supporting the needs of modern applications. This is about the conclusion of this video. Thank you everyone for being a part of this video. See you soon in the next video. Thank you.